Hello friends, I welcome you in lecture number 29 on Laplace transform. In this lecture we will discuss this problem on finding the inverse Laplace transform of this function. Given function is s divided by s raised to 4 plus s square plus 1, and we can see this is a rational function. So first we will try to factorize this function in the denominator, which is s raised to 4 plus s square plus 1. And if we observe, this is not a perfect square, so we can try to find out middle term for this function so that we can write it as a square of some another polynomial in s. So for that we can use this formula to find out middle term. We know that square of middle term is given by 4 times first term into last term. Here first term is s raised to 4, last term is 1, so we have 4 times s raised to 4 times 1. Therefore middle term equal to plus or minus 2 times s square, because this we can rewrite as square of plus or minus 2s square. So either we can write 2s square as a middle term or minus 2s square as a middle term, but we will write 2s square so that we can factorize this in terms of quadratic polynomials in s. Here I write 2s square, and to set this s square I have to subtract s square from 2s square. So these two are equal now. So we have rewritten our function in this form. We are adding 2s square, and here we have s square, so we have to subtract s square. So now we can observe that this bracket is the square of s square plus 1, and we have minus s square. So if we use the formula of a square plus b square, we will have s square plus 1 plus s times s square plus 1 minus s. Therefore we have rewritten our function s raised to 4 plus s square plus 1. This we obtain as a sum of two quadratic factors, s square plus s plus 1 times s square minus s plus 1. And these two quadratic factors cannot be further factorized into linear form. Now our function is s divided by s raised to 4 plus s square plus 1. So now we rewrite our function. Our function is s divided by s raised to 4 plus s square plus 1, and this is equal to, we replace this by product of these two quadratic factors, s square plus s plus 1, s square minus s plus 1. So we have product of two quadratic factors in the denominator. Now we can use either partial fraction method. We can write this as s square plus s plus 1, and here we will write polynomial of degree 1, say as plus b. Similarly we will write s square minus s plus 1, and in the numerator we will write cs plus d, and then we can decide these constants a, b, c and d. What another way is, we can think of difference of these two. If we take difference of these two, s square plus s plus 1 minus s square minus s minus 1, then let's see what we obtain. This is minus s square plus s minus 1. S square will cancel out, s is 2 times, so we have 2s, and 1 will cancel out. So we observe that difference of these two is 2s, and here we are having s in the numerator, and 2 we can multiply by 2 and we divide by 2, and we can write this 2s. Instead of 2s we will write difference of these two. So it is not necessary to go by this method. instead of going in this way, we will write 2s, we will set 2 here, this we will write as 1 by 2 times 2s, and 2s will be replaced by difference of these two quadratic factors. So we are not using this method of partial fractions because it is here possible to write down 2s as the difference of these two quadratic polynomials, and this will be possible if two factors in the denominator are of the same degree. Here we have two polynomials of the same degree, and therefore it is possible here. So s square plus s plus 1, s square minus s plus 1, and 2s is replaced by s square plus s plus 1 minus s square minus s plus 1, and this we can rewrite as 1 by 2. This is 1 divided by s square minus s plus 1 minus s square minus s plus 1 divided by s square plus s plus 1. This is cancel out. Here I will have to write down 1. So I am taking in this way s square plus s plus 1 divided by this, that will cancel out s square plus s plus 1, and similar way s square minus s plus 1 will cancel out here, and we will have 1 divided by s square plus s plus 1. Now these two are irreducible polynomial. So if you recall, we have discussed the method for finding inverse Laplace transform of this type of functions in which we have irreducible polynomial in the variable s of second degree. So for this we can set last term. If we find out last term will be equal to middle term square. Here middle term is minus s divided by 4 into first term is s square. So this is going to be 1 by 4. So last term, if we consider 1 by 4 is as the last term, then we can write this as square of s minus 1 by 2. So we will add 1 by 4 and we will subtract 1 by 4. Same thing here. Here also middle term must be last term must be 1 by 4. If we go in this way, instead of minus s, here middle term is s. So we will have 1 by 4 as the last term. So that we can adjust. We add 1 by 4 and we subtract 1 by 4, and we try to rewrite this function in another form so that we can have the formula for the inverse Laplace transform. So in the next step we consider this is 1 divided by s square minus s plus 1 by 4 and plus 1 minus 1 by 4. So because I am adding 1 by 4, I have to subtract 1 by 4. Same thing I will do here. S square plus s plus 1 by 4 plus 1 minus 1 by 4, and this now we can rewrite as this is equal to 1 by 2 1 divided by this first 3 terms can be written as square of s minus 1 by 2, and this is going to be 4 minus 1, that is 3 by 4. Similarly here we have square of s plus 1 by 2 and plus 3 by 4, and this we can again rewrite as we keep s minus 1 by 2 as it is, s minus 1 by 2 square plus 3 by 4 can be written as root 3 by 2 whole square minus 1 divided by s plus 1 by 2 square plus root 3 by 2 whole square. Now we recall what is the formula for inverse Laplace transform of this type of function. Our function is in this form: 1 divided by square of s minus a plus square of b, and we have seen this function has inverse Laplace transform because we have s minus a, we will write e raised to at, and if you observe, if we replace s minus a by s, we have 1 divided by s square plus b square, and inverse Laplace transform of this function is sin bt divided by b. So we will apply this formula here, and we will be able to write down the inverse Laplace transform. So therefore L inverse of s divided by s raised to 4 plus s square plus 1 equal to 1 by 2 times L inverse of this first function. If we compare with this, we have a equal to 1 by 2, so we have e raised to t by 2, and b equal to root 3 by 2. So we have sine of root 3 by 2 into t divided by b. Here b is root 3 by 2. Similarly, if we compare this function with this function, value of a is minus 1 by 2, therefore we have e raised to minus t by 2, and this is same. Here b equal to root 3 by 2, sine root 3 by 2 into t divided by root 3 by 2, and we can observe that this 1 by 2 will get cancelled, and we have this portion, we rewrite this as e raised to t by 2, and this sine root 3 t by 2 divided by root 3, this part is common, so we can write this as e raised to t by 2 minus e raised to minus t by 2 into 1 by root 3 times sine root 3 t divided by 2. So this part we have taken common, sine root 3 by 2 divided by root 3, that quantity is common in both the terms. This 1 by 2 will cancel out with this 1 by 2, and we have e raised to t by 2 minus e raised to minus t by 2. Now this we can rewrite. If you observe, we can rewrite this as we can use the definition of sine hyperbolic function. If we have sine hyperbolic t, we have e raised to t minus e raised to minus t divided by 2. Now instead of t, we have t by 2, and we don't have 2 here, so that we can adjust here. We can multiply by 2 and divide by 2. Here we have e raised to t by 2 minus e raised to minus t by 2 divided by 2, and we write this 1 by root 3 here, and in the product we write sine root 3 by 2 into t, and now this bracket is nothing but value of sine hyperbolic function at t by 2 into sine root 3 by 2 into t. So sine hyperbolic t by 2 times sine root 3 t by 2 times 2 divided by root 3. So in this way we can find out inverse Laplace transform of this type of functions, and here we are not using that partial fractions like as plus b divided by s square plus s plus 1. Instead of this, we are able to write down our function directly as a sum of partial fractions by writing this 2s equal to difference of these two polynomials. So whenever we have quadratic polynomials, polynomials of the same degree, either quadratic or linear. Suppose I have polynomials of second degree in the product, or polynomials of third degree in the product, or linear polynomials in the product, then I will check whether it is possible to write down this numerator as a difference of these two or not. Here it is possible to write down this 2s as the difference of these two. So first I have written 2s equal to difference of these two, and I am directly able to write this function in terms of partial fractions. And because these two are irreducible, we first set the last term so that we obtain this form, and we are able to apply this formula. So this is all about this session. I hope you like it. Thank you very much.